Welcome back. Up to this point, we've been talking about ways to describe variables. For example, I talked about training for the 204-kilometer epic bike ride along the Great Ocean Road. This graph here describes the distance of my long training rides. When we look at this distribution, we're describing a single variable, the distance of each of my long training rides. We can call this a univariate distribution. Uni meaning one, so we're describing a single distribution here. This might be interesting enough, and we've gone through all these weeks showing ways that we can describe things, and it's certainly something that we want to do in any analysis. But we can start to ask even more interesting questions when we start looking at two or more variables. For instance, when I was training for my bike event, some of my rides were fast while others were slow. Why was this? Could we explain the difference? Now, by experience, I can tell you that my speed was affected by several things. How many hills I had to climb, how strong the wind was, that was a big one, and whether or not I had mechanical or other difficulties, such as the time I put a hole in my tire or a time that I ended up with heat exhaustion and barely made it home. Now, in these cases, we're talking not only about a single variable, such as how fast the ride is, but another variable as well. In this case, we're talking about what's called a bivariate distribution, or the joint frequency of two variables. Correlational research is a whole area of study that lets us look at the relationship that naturally occurs between two variables. It's an entire area of study, and actually much of my research is focused on correlational relations between different things. For example, is there a relationship between how fast I ride and the number of hills I climb? From experience, I'd say there certainly is that when I'm doing a lot of climbing, I'm going much slower than when I'm riding along the coast. It's fairly flat and I can get some pretty good speed going, although the wind has something to do with that as well. With correlations, we're not manipulating anything, but we're just looking at the relationships that are there. And it's used a lot in the social sciences. So it's something that you'll read a lot, and it's very useful as an approach to research. Now, one thing I'll mention with correlation, we're looking at relationships, and although sometimes we'll start to talk in an almost causal manner, correlation does not equal causation. Here's a cute PhD comics that gets at this. And it captures this idea that there's a relationship between things, but it's not actual causation. Let's look a bit more at this idea of correlations. Here's a set of numbers, and this is actually made up data for the purpose of example, but let's say for each of my long training rides, I have the average speed in miles per hour and the number of feet that I climbed throughout the course of the ride. And in each case, the numbers are paired together. So for instance, when my average speed was 13.2 miles per hour, it was the ride where I climbed 2,800 feet. To visualize this, we can create what's called a scatter plot. We see that the length of my average distance or my average speed is along the x-axis. And then the feet climbed, or how much climbing I did, is along the y-axis. Each of the points is a pair between the average speed and the distance gone. So for instance, on a ride where I averaged 13.5 miles per hour, I climbed 2,500 feet, whereas on another ride, I averaged 16.9 miles per hour and only climbed 380 feet. Now, with correlation, we're asking what's the linear relationship, if there is one, between two variables. Looking at this graph, think about if you were to draw a line that best fit the data, what line would you draw? Here's my estimate. We see it's a pretty clear negative relationship, such that as the distance climbed increased, my speed seemed to go down, and my speed got faster when there was less climbing there. Not always, there was some variance there, but in general that's what we see. Whenever we're considering the correlation between two variables, we can think about, is there a positive relationship, a negative relationship, or really no relationship? For instance, this graph depicts a positive relationship between two variables. We see that as the values go up on the x-axis, they also go up on the y-axis. Some common examples of this, one thing I've noticed is as the weather gets nicer, more people spend time outside. As I spend more time biking and running, I get to be in better shape. We actually see that studying and attending class tends to relate to scoring better on exams. And for some people, the more stressed out they get, the more chocolate they eat. You can think of what might be true in your case. This graph shows a negative correlation between two variables. As our x-axis goes up, the y-axis goes down. Going back to my cycling example, as the wind increases, my speed tends to go down because it's hard. Other common examples, as the temperature goes down, I tend to wear more clothes. I get cold easily. As stress increases, happiness often decreases for many people. Spending more time with family and friends, loneliness levels will go down. So we see an inverse relationship there. This final graph shows no relationship between the variables. There's no real sort of positive or negative relationship there. Knowing something about the first variable tells me nothing about the second one. These graphs tell us the direction of the effect. Is it positive or is it a negative? Another thing we might want to know is how big is the effect? How correlated are these variables with one another? For example, if I were to ask you on a scale of 0 to 100 how physically fit you are, what would you say? Now, I might say, okay, maybe a 70, someone else might say a 40. The scores are going to be all over the place. We can draw a circle to represent the variance in physical fitness. And so we can think the middle is the average, and then people vary all around that number. Not everyone is the same, and so we can look at this variance. Now, here's a second variable, mental well-being. Again, I could ask you on a scale where you stand, and people would be kind of all around. Now, we can put these two variables together and say, is there a relationship there? Here, we have physical fitness and mental well-being. They're not overlapping at all. So knowing something about your physical fitness level tells me nothing about your mental well-being. In this instance, there's a little bit of overlap between the two variables. So that if I know something about your physical fitness, there's a little bit of a relationship with mental well-being, but not very much. And then we have this one, which actually looks something like a beach ball. This is a high correlation, and so there's a lot of overlap between these two variables, and such that knowing your physical fitness level tells me, there's something I know more about what your mental well-being might be. So in this case, there's a lot of overlap in the variance of these two variables, or there's a high correlation. So we can talk about high versus low correlations. To formalize this a bit more, we have a specific statistic that we use, which is called the Pearson-R correlation coefficient. It's a descriptive statistic that was named after a guy named Pearson, thus called the Pearson-R, and expresses the degree of relation between two variables. Next time, I'll talk specifically about how to calculate this, but the key right now is that it gives us an indication of how correlated two variables are. To interpret this, we want to look at the absolute value. So an R goes from -1 to +1. Numbers close to 0 indicate a low correlation, so they're not very related to one another, whereas values closer to 1 is a strong positive correlation, and values close to -1 are going to be a strong negative correlation. So for strength, we want to look at the absolute value, how close to 1 it is versus 0, and for direction, we can look at the sign there. Now, years ago, another guy named Cohen came up with a rough guide for interpreting this R correlation coefficient. He said that 0.1 would be a small effect, 0.3 would be a moderate effect, and 0.5 and above would be a strong effect, or kind of around 0.5. Now, this is just a rough guide, and we'll come back to this idea about how big an effect is, but it does give us some indication of things. Just to get a sense of things a little bit, here's a little bit of practice. Look at each of these. We can think about, and this is made up data, but time spent studying and exam scores. How would you describe that correlation? And here are a few others as well. Here's what I got. Time spent studying and exam scores is R equals 0.12. That's pretty close to that 0.10, so it's pretty small. It's closer to 0 than to 1. There's no negative sign, so it's a positive correlation. So in this case, there's a small positive correlation such that the more time you spend studying, higher the exam scores are. With cigarettes smoked and life expectancy, there's about a moderate negative correlation such that as the number of cigarettes smoked increases, life expectancy decreases. And in height and weight, it's a fairly high positive correlation such that those who are taller often weigh more. Again, this is not causation, we're just looking at the relationship between two variables. Next time, we'll look at how to calculate correlations, but hopefully this gives you a bit of conceptual background for thinking about the relationship between two variables. Thanks for listening. See you next time.